All right, let's go ahead and pick up our next example of x-intercepts. And for x-intercepts, we want to keep working our process. We don't want to jump in and just set the numerator equal to 0. Although it's really easy to just look right there and be like, hey, x equals -1, that's an x-intercept, right? Well, maybe. I don't know. We've got to get down to step 4 to make that decision. So to do that, we've got to factor the denominator and see if there's any issues down there with -1. Now, one possibility is you could just go ahead and plug in -1 right here and see if it makes the bottom 0. If it does, then you don't use that. And if it doesn't, then you're good. But we'll work our factoring process to keep things the same here. So 3 factors out x squared minus 9x minus 10 is what the trinomial is. And if I use the magic x here, I get a -10 on top and a -9, which means my magic numbers are -10 and +1. This denominator factors to be x minus 10 times x plus 1 with a 3 out in front. So if I rewrite this, I get x plus 1 over 3 times x minus 10 times x plus 1. And right away, I can see that this binomial x plus 1 and this x plus 1 on the top and the bottom are the same thing. Anything divided by itself is 1. So this real function, simplified version graph, would look like 1 over 3 times x minus 10, which is why I don't jump in at the beginning and find my answer. I have to be careful to recognize it actually comes right here. And I look at my numerator and say, what could make the numerator 0? Well, the numerator is 1. There's no variable up there anymore. So the remaining numerator, if I set that equal to 0, I would say, wait, that 1, that's not 0. And I would stop and say, that's false, which means it can never be 0. So there is no x-intercept. What I thought was going to be an x-intercept at the beginning turns out to be a hole because it factored and reduced out.